Hello, everybody. Since this is the first meeting with you, before starting any special topic, I would like to make an introduction to geotechnical engineering. In this way, you will have an idea about what the geotechnical engineers do, why, where, and when we need the knowledge of geotechnical engineering. Here we go. In his or her practice, the geotechnical engineer has many diverse and important encounters with soil. He uses soil as a construction material. She uses soil as a foundation to support the structures and embankments. She must design structures to retain soils from excavations and underground openings. He phases soil in a number of special ways, such as collapse, liquefaction, swelling and shrinkage, and frost heaving. Several examples drawn from actual jobs will be described in order to illustrate the types of problems and their solution that a geotechnical engineer provides. Here is the first example. In this project, it was planned to construct a flexible highway pavement in a desert 400 passes per lane per day for a vehicle with maximum wheel load of 67 kilonewton. The geotechnical engineer responsible for this project carefully studied the case and decided that the best possible and economical way was to use in situ soil as a construction material. In the figure here, you see the cross section of highway pavement. It mainly consists of 4 layers as illustrated here. They are subgrade, subbase course, base course, and surface course. Subgrade was the in-situ desert, and subbase course was made by compacting the top 150 millimeter of in-situ soil. And the base course was made by mixing sand and Portland cement. The mixture was brought to a proper moisture content and compacted with a suitable equipment, and the thickness of base course was 150 millimeter. Finally, the top layer, surface course, was made by mixing hot asphalt with sand, and the thickness was 50 millimeter. The geotechnical engineer faced a lot of crucial questions regarding this project. Let us see what they were. The first one, how thick should the layers of the pavement be to carry the traffic load? Secondly, what was the optimum mixture of additives, namely asphalt, cement, for the stabilization of desert sand? The third question, was the desert sand preferable one for the construction of surface course? And the fourth question, what grade and weight of asphalt would make the most economical and satisfactory surface course? Finally, what type and how much compaction effort should be utilized? That's it. Let us move to the next slide. This is the second example for the usage of soil as a construction material. In this project, it was planned to build a structure to hold a large amount of water, about 6,000 cubic meter per hectare per 120-day dry season for the irrigation of wheat-grown fields. The geotechnical engineer studied this project and decided that the desirable solution was to construct an earth dam. It was popular for two major reasons. First, it was cost effective, which means it was economic. Secondly, the clay and rock materials required for the construction of earth dam were ample in the surroundings of dam site. The burning questions that had to be answered by the geotechnical engineer regarding this project were as follows. The first one, what should be the dimensions of the dam to give the most economical and safe structure? This was important for the whole stability of earth dam. The second question, what was the minimum safe thickness for the rock fill? If you look at the figure, you will see rock fill materials on both sides of the clay core. They provide stability as well as protection for the clay core in the middle, as you see here. Third question, what moisture content and compaction technique should be used to place gravel and clay layers? Now, earth dams cannot be constructed at once. They are constructed layer by layer. Each layer should have a proper thickness and moisture content and be compacted by a suitable equipment. The fourth question, what would be the time-dependent strength and permeability properties of the constructed dam? This was another important point because dams are constructed for a given period, which means the sustainability of the earth dams are important for the predetermined time. They should function properly for that period. The fifth question, which is another important one, how much leakage would occur under and through the earth dam? Now, we want the structure to hold a considerable amount of water behind it. And we don't want much of the water to be lost through leakage. Now, let me show you two leakage patterns for earth dam. The first one was through earth dam. Now, if you follow the red line, this is the seepage path through earth dam. And the second one, beneath earth dam. There you have it. That's it. Let us go to the next slide. These examples and the next one are for the second category, that is to say, using soil as a foundation. The purpose of the project was to provide a suitable and affordable foundation system for a university building. And the solution was partial flotation technique. Now, before defining what the partial flotation is, let me give you some information about the project. Had these buildings being placed on the ground surface, having a soil profile as illustrated here, there would have been a great settlement and bearing capacity failure. The engineer studied the case very carefully and decided that the building should be placed in excavation because he also studied the relative economy of shallow foundation versus deep foundation. Now let's come back to the partial flotation technique. If the weight of a building is reduced by removing soil, the technique is called flotation. If it is partly compensated, it is called partial flotation. That was the case in this project. When entirely compensated, it is called full flotation. Now, the total weight of the building, including dead loads and live loads, was 330 meganewton, and the excavated weight soil was 258 meganewton. So the net load applied to the ground was 72 meganewton. So the load applied to the ground was reduced substantially in this way. The geotechnical engineer had to answer several important questions. Let us see what they were. The first one, how deep into the soil should the building be placed? In other words, what would be the depth of excavation? The second question, would the excavation have to be retained by a special retaining wall to prevent the cave-in of soil? Third question, would it be necessary to lower the groundwater table? This was important because it is necessary to carry out the excavation and the construction of foundation in a suitable environment. If that was the case, what might have been the technique to lower the groundwater table? Fourth question, was there a danger of damage to surrounding buildings? Due to excavation, the surrounding buildings may undergo lateral movements or differential settlements. This was another important point. The fifth question, how much would the completed building settle, and would it settle uniformly? Well, this case was eliminated due to the application of partial flotation. Finally, for what stress and stress distribution should the foundation be designed? This was another important question. That's all. Let us now move on to the next example. In here, the idea was to construct an oil storage tank of 15 meter in diameter and 17 meter in height on a very soft, compressible clay soil. And the solution was to use the preloading technique. Now, had these oil storage tank, as shown in the figure, been placed on the ground surface without any special foundation, a settlement of about 150 centimeter would have taken place due to soft underlying soil. This amount of settlement was too much to be tolerated. So the geotechnical engineering studies showed that a very economical way to the oil storage tank foundation was to use the preloading method. The preloading method consists of building an earth embankment on the ground surface to compress the soft clay layer, as illustrated here. removing the earth embankment, and finally placing the oil storage tank on the prepared ground surface. Here are the burning questions that had to be answered by the geotechnical engineer responsible for this project. The first one, how high a field could be placed? Well, this depends on the bearing capacity of soft clay layer, because the soft clay layer has a very low permeability. When an embankment built on it, excess pore pressure will develop, and the drainage of or the dissipation of excess pore pressure will take time. So immediately after loading, the undrained conditions will prevail. This is a very critical situation. The second question, how fast the fill could be placed. This, of course, depends on the availability of the earth material to construct earth embankment and the technique used. The third question, what were the maximum slopes for the field? Now, the angles of the slope, as shown here, are very important to sustain the stability of the earth embankment built on the ground surface. The fourth question, could the field be placed without employing special techniques? Again, this is something to do with the bearing capacity of underlying soft clay layer. Since immediately after construction, the undrained condition will prevail, then the bearing capacity of soft clay layer will be a critical one. In that case, you may use geotextile spread over the ground surface to increase the stability of the embankment and the bearing capacity of the soft clay layer. Things like these can be applied. And fifth question, how much would the field settle? As the clay layer compresses, the earth embankment will settle as well. But we want the earth embankment to stand without fail, even it undergoes settlement. The sixth question, how long should the field be left in place so that the foundation be compressed enough to permit construction and use of the tank? This is something to do with the project timing, because construction and removing of the embankment will take time. It may take several months, even a year. That's all. Let us go to the next slide. This example and the following one are for the third category, that is to say, designing structures to retain soil. In this project, the aim was to build a cargo loading platform with a crane moving on rails as part of a ship loading dock. Now, the solution was an anchored retaining structure. Ships, as shown here, are brought alongside with retaining structures and loaded with cargo stored on the land side of retaining wall, and the loading is done by a crane moving on rails parallel to retaining structure, as shown here. The following were the important questions to be answered by the geotechnical engineer. The first one, what type of wall should be used regarding material cross-section. Second question, how deep must the wall penetrate the foundation soil to prevent the wall from kicking out at its base? Now we are talking about the lower portion of retaining structure as shown here. This portion should have a sufficient penetration depth. Otherwise, it will be moved forward due to pressures acting behind the retaining structure. And if it moves, then the structure will fail. We don't want this. The third question, at what height on the wall should the anchors be located? Now, positioning of the anchors are also important in the design of anchored retaining structures because they provide necessary resistance for the retaining wall. And fourth question, how far from the wall should the anchor ties extend? Since the resistance is dependent on the penetration of anchors into the ground, the total length is very important. As we said, these will provide resistance, additional resistance for the retaining structure. And fifth question, what type of anchoring system should be used? There are several types of anchoring systems, but in this project, the grouted anchoring system was adopted. Sixth question, how close the wall should the loaded crane be permitted? This is another important point. Now, the distance from the edge of the retaining wall was important for the crane to move forward and backward safely. The final question, what was the distribution of pressures acting on the wall? Now, to design any retaining structures, we need to determine the loads acting on it, and these are dependent on the pressures acting on the wall. Now, regarding hydrostatic pressure, if we think that the level of water behind the retaining structure is the same as the one in front, then the hydrostatic pressure in this case will cancel each other out, and we will have passive resistance, in other words, passive earth pressure in front of the wall as shown here, and the active pressure behind the wall. Okay, now in addition to these, we have also surge charge loading on the surface due to crane and the cargo stored on the platform. That's it. Let's keep on. The goal of this project was to shorten the motorway route available between two commercial cities. The solution was to use a tunnel through a mountain halfway between these two cities. Now in the section you see in the figure you see the cross-section of the tunnel. Let me give you some information about it. The initial lining, as shown here, is also called primary lining. It is used to secure the work site during construction. Another lining is waterproofing lining. Now, this is sort of watertight membrane. It prevents the infiltration of groundwater into tunnel, and it is located between initial lining and the final lining. Now, final lining is reinforced concrete. The first step in the construction of final lining is to pour the concrete of inward slab as shown here. This is the inward slab segment of the whole final lining system. Now, the first step is to construct these before lining the rest of the section. And sidewalk, they are available on both sides as shown here and here. They are for people to walk in emergency. And fire water pipe located here. Now, this is for putting out the fire if the fire breaks out under the rain. This is also available on both sides, as you see here and here. This is for the drainage of water that may accumulate in tunnel. And the power conduit. This is for the lightening of tunnel. And the jet fans shown here, they are for the ventilation of tunnel. Shoulders on both sides, they are emergency parking places. Now, let us see the question that had to be answered by the geotechnical engineer regarding this project. The first one, what methods were to be used to drive the tunnel considering different sections? Well, from one end to another, you may come across different soil and rock conditions. Therefore, for each one, you should provide a different driving method. The second question, what type of tunnel support should be applied for each section? Again, these will depend on the soil and rock conditions. Due to them, the shotcrete strength, the number of anchors will be decided. And third question, what would be the stresses and deformation be for the unlined as well as the lined tunnel? Now, when you make an opening in the ground, there will be stress concentration around this section. And these will cause deformations as well. So we want to know what the magnitudes of stresses and deformation will be unlined, which means without support and with support. And the fourth question, what was the dimensioning of the tunnel support for immediate phases and final cases? Again, this is related with the stresses and deformation as defined in the third question. The final question, what would be the methods for waterproofing or drainage if required? Now, we explained what the waterproofing is. These can be carried out usually with a watertight membrane, as explained before. And the drainage system, these may be provided by piping or pumping system, depending on the conditions. Now, how do you feel? If you feel bored, we can have a break. Otherwise, we can continue. What do you think? Right. Let us move on to the next slide. Now, we have come to the final categories examples. That is to say, you meeting soil in a number of special problems. In this project, the aim was to prevent the residential houses from the damage of expansive soil. Now, expansive soils are very problematic soils in geotechnical engineering because when they get in touch with water, their moisture content increases, and as a result, the volume increases. But when they lose water, their moisture content decreases. As a result, volume of the soil decreases. So these phenomena, contraction and expansion, will cause structures to move upwards and downwards and will damage the structures as a result. The expansive soils are almost everywhere in the world, but most commonly in arid and semi-arid regions. And there are several methods to overcome this problem, but in this project, the smart application was waffle mat foundation. If you look at the lower portion of the figure, you will see the details of waffle mat foundation. Now it contains waffle boxes as shown here. The idea behind the waffle boxes is that when soil expands, it expands freely into the voids. And the pressure in this way is substantially reduced. Regarding this project, the questions that had to be answered by the geotechnical engineer were as follows. The first question, how much would the ground heave upon wetting? We should know the amount of expansion of the soil. These may be 10 times as much as its original volume. But the expansion of soil can be experimentally determined in the laboratory. The second question, would the ground heave be uneven? An important point, because when the uplift pressure concentrates in some part of the building, as shown here, then there will be a differential movement. This will cause the building to fracture. The third question, how much pressure would the ground exert upon swelling? This is another important issue, because if we know the uplift pressure inflicted by the soil, then we can arrange the foundation accordingly. Now, if the stresses beneath foundation are greater than that of soil, then there will be no special arrangement. However, if the uplift pressure is greater than that of foundation stresses, then the structure will damage because it will move upwards. And as explained earlier, if the pressure localizes in one part of the foundation, then there will be differential movement. This will cause structure to fracture. Right. The fourth question, should there be any drainage system around the foundation to prevent surface water infiltration into the soil? This is a good precaution to be taken around the foundation system. It will prevent the penetration of surface water. The fifth question, what method should be chosen to avoid swelling damage to the structure? As I said, there are several methods, but in here, waffle mat foundation was chosen. And in earlier explanation, we said that there may be several possible solution methods, but we should choose the economic one among the best possible solution. So when you compare these with mat foundation, you can easily understand that in here you will use less concrete, less reinforcement. The final question, what should be the dimensions of waffle boxes of foundation? Yes, this will depend on the magnitude of expansion of soil. And the boxes dimensions will accordingly be determined. That's it. Let's move on to the next example in this category. Here we have a second example for special soil problems. In this project, it was planned to protect the piers of a highway bridge from the damage due to soil liquefaction. Soil liquefaction is a very special problem in geotechnical engineering. When the saturated sandy soils are subject to shaking, they tend to compress, and this compression will apply pressure to the pore water. As a result, the pore pressure will increase, which is named as excess pore pressure. When the excess pore pressure equals the total stress of soil, effective stress becomes zero. That is to say, the shear strength of soil is lost, thus the bearing capacity. So the structures over these soils will collapse. They may undergo tilting, overturning, or sinking into the ground. Of course, there are several methods to treat the soil liquefaction. We may either treat the soil or arrange a special foundation system against liquefaction damage. In this project, the solution was to place the piers on piles, passing through the liquefiable soil and resting on cohesive soil layer, as shown here. The layer here is the liquefiable one, and you see the piles passing through and resting on cohesive soil. The important questions that had to be answered by the geotechnical engineer were as follows. The first question, what would be the magnitudes of lateral forces acting on piles, especially during liquefaction as illustrated here? The second question, what would be the magnitudes of lateral displacements of piles during soil liquefaction, and would they be acceptable? Now, you see the displacement of the piles. When the soil liquefies, there will be an increased lateral forces on piles. And we should secure that the lateral displacements of piles are limited. Otherwise, the bridge deck slab, as shown here, may collapse. The third question, what would be the magnitudes of vertical settlements of piles, and would they be tolerable? Now, in addition to lateral displacements, piles may settle vertically, as shown, and this should be limited as well. Otherwise, excessive settlement dysfunction the bridge. The fourth question, would there be a stability problem around the abutment of the bridge? and what type of measure should be taken if required. Now we are talking about this section of the bridge. Now when the soil liquefies, the stability of the fill will be disturbed. And if the fill slides, additional forces will be on the piles. And these may, of course, disturb the stability of bridge. It may cause the bridge to collapse or displaces laterally. And this will dysfunction again the bridge. We don't want this. If the piers are not necessary for the stability of the fill, then we should take additional measures to stabilize the sliding mass. The fifth question, the final one, what should be the number, diameter, and the embedding depth of piles into the cohesive soil? Now, this portion is called the embedded depth. So these were very crucial questions that had to be answered by the geotechnical engineer. To solve any geotechnical engineering problem, we need geology, experience, economy, and soil mechanics. Last but not least, the engineering judgment. Let us see briefly what they are. Geology aids the geotechnical engineer because the method of formation of soil mass influences its size, shape, and behavior. Experience improves the reservoir of geotechnical engineer by comparing the predicted behavior of a structure with the measured performance. Economy, on the other hand, is the important ingredient in the selection of best possible solution among available ones. Soil mechanics is the science underlying the solution of a problem. Now, the interpretation of insufficient and conflicting data, selection of parameters for geotechnical design, and modification of a solution require experience and engineering judgment. While a sound knowledge of soil mechanics is essential for the successful geotechnical engineer, the engineering judgment is the characteristics that distinguishes the outstanding geotechnical engineer. That's all, folks. I appreciate your attention